Hello students, welcome to my channel Arun's Physics Portal. In this lecture, I will be talking about the motion in a straight line and motion under gravity. This topic is meant for class 11 students of CBSE, ISC and different state boards. The topic covered here will also be found useful for various competitive exams like NEET and JEE Mains. The complete note of the topic is given here for your convenience. I hope you enjoy going through it. Now let us come to the topic. In this lecture, we are dealing with the motion of objects having constant acceleration. Let a particle starts moving along a straight line with initial velocity u at time t equal to 0. It has a constant acceleration a and it has a final velocity v after a time t. Then the instantaneous acceleration is given by a equal to dv upon dt. This gives you dv equal to a times dt. To find the total change in the velocity, we integrate equation 1. Thus we have integrating both sides of equation 1, we have integral of dv. Limits vary from u to v. V is the final velocity and u is the initial velocity. This is integral of a dt. Time varies from 0 to t. That means the velocity is u when time is 0, velocity is v when time is t. As time changes from 0 to t, we see that the velocity of the particle changes from u to v. We evaluate the integral in equation 2. So we have, this is the integrated value. So this gives you, put the limits here. This is v minus u equal to a into t, or v equal to u plus at. So if you know the initial velocity, you can find the final velocity of the body after time t, provided you know the acceleration. So equation 3 can also be written as dx upon dt. What is velocity? Velocity is the rate of change of displacement. If x is displacement, then dx upon dt gives you the velocity. So dx upon dt is u plus at. Or we can write this equation as dx equal to u times dt plus at dt. Now integrate this equation from time limits from 0 to t and value of x varies from 0 to x. Okay, so this is equation 4. As the time varies from 0 to t, the distance of the particle from the origin changes from 0 to x. Here, x does not represent the total distance covered by the particle in time t. The particle might have covered a distance quite different from x, but at time t, it is at a distance x from the origin. So evaluate the integral. This is so simple, and the integrated value gives you x equal to ut plus half at square. Okay. Equation 5 can also be written as x equal to, within bracket, u plus half at into t. Take out t common from this expression, you get this result. So this gives you 2u plus at into t upon 2, or this is equal to u plus at into t upon 2, where u plus at is nothing but v. So we have x equal to u plus v upon 2 into t, where we have used equation 3. Now square both sides of equation 3. We have v square is u plus at whole square. This is u square plus 2u at plus a square t square, or v square is u square plus, take out 2a common from these two terms. So this is 2a into ut plus half at square. Ut plus half at square is x. So this gives you v square is u square plus 2ax. Equation 7 can also be directly deduced as shown below. We have a equal to dv upon dt, a rate of change of velocity is acceleration. I can write it as dv upon ds into ds upon dt. So ds upon dt is the rate of change of displacement. This is nothing but the velocity. So this can be written as dv upon ds into v, or we can write v times dv is equal to a times ds. Integrate both sides. So this gives you integral of v dv limits varying from u to v equal to a times integral of ds. The limits vary from 0 to s. We have taken a outside the sign of integral because of the fact that the acceleration is a constant. So integrate it, put the limits, we get v square minus u square upon 2 is equal to as. To clarify this equation, we write this one as v square by 2. Put the limits here, limits are v and u. This is v square minus u square upon 2. Okay, or we can write v square minus u square upon 2 is as, or v square is u square plus 2as. The distance xn covered by the particle in the nth second of its motion is simply equal to the difference of the distances covered by the particle in n seconds and n minus 1 seconds of its motion, and can be found using equation 5. Remember that nth second is a particular 1 second. Okay, suppose you are standing in a queue, okay, for a movie ticket. Okay, so this is the counter. One person is here, one is here, one is here, and one is here. Okay, you are here. So this is the first one, this is the second one, this is the third one, and this is the fourth one. So first man, second man, third man, fourth one. You are standing at the third position. You are only one. You are not three. You are only one. Similarly, nth, you are third. Similarly, nth means only one particular second. This is 1 second, but that is particular. It may be 5th second, it may be 8th second, or it may be 11th second. Okay. So xn, let xn be the distance covered in n seconds minus distance covered in n minus 1 second. Write the expression for distance covered in n seconds is un plus half an square. Recall that x equal to ut plus half at square. In place of t here we have n. So this is un plus half an square minus u times n minus 1, because t is here, n minus 1. Okay, plus half a n minus 1 whole square, or xn is equal to un plus half an square into un minus u from here plus half a n square minus 2n plus 1, or xn is, this un will cancel out with this un. This is half a n square with a minus sign, is half n square with a plus sign. So these two will also cancel out. So you are left with minus minus gives you plus. So u plus 2n minus 1 upon 2 into a. This is simple mathematical manipulation. You can easily get this result. Okay. So let me emphasize that the nth second is always denotes a particular 1 second. For example, if a particle covers a distance of 5 meters in 4 seconds, 7 meters in 5 seconds, and 10 meters in 6 seconds of its motion, then the distances covered by it in the 5th and 6th seconds of its motion are respectively 2 meter, 7 meter minus 5 meter, and 3 meter, that is 10 meter minus 7 meter. It covers 5 meter in 4 seconds and 7 meter in 5 seconds. So distance covered in the 5th second is total distance covered in 5 seconds minus distance covered in 4 seconds. That is 7 meter minus 5 meter, and that is your 2 meter. Okay. So equation 3 to 8 are applied in solving problems of motion along a straight line with constant acceleration and are given in table 1. If the acceleration is negative or the body is retarding, we should replace a by minus a. All these equations are applicable only when the acceleration a is constant in magnitude and direction. Okay. Table 1 presents here the different equations of motion in a straight line with constant acceleration. We now come to an example. The distance x covered by a particle is given as a function of time t as t equal to ax square plus bx, where a and b are constants. So find what is the acceleration of the particle. So we differentiate this equation with respect to time. So this gives you 1 equal to 2ax dx upon dt plus b times dx upon dt. So here we have dx upon dt common. So we can write it as 2ax plus d 2ax plus b into dx upon dt. Now dx upon dt is nothing but v. So we write here as 2ax plus b into v. Okay. So this gives you the value of velocity. So v equal to 1 upon 2ax plus b. Okay. So we have to find the acceleration. So acceleration is the rate of change of velocity. Because in this expression do not have t. So we must somehow introduce t in this equation. How we do that? This is like this. We differentiate dv with respect to t. So this is dv upon dt. You can write it as dv upon dx into dx upon dt. Okay. Now dx upon dt is here. Okay. And differentiation of v with respect to x from here gives you minus 2a upon 2ax plus b whole square. So this is minus 2av upon 2ax plus b whole square, or the acceleration dv upon dt is minus 2a. This is nothing but v. Okay. This is 1 upon this 1 upon 2ax plus b is nothing but this is equal to v. So this is 1 upon 2ax plus b whole square. So this is v square. Okay. So this is here minus 2a into v cube by using equation 1. So we found the acceleration of the particle. We now come to motion under gravity. If a body is allowed to fall freely under gravity from height h, where h is 2 less than the radius of the earth, then the body falls almost in a vertical line with constant acceleration if the resistance of air is neglected. This constant acceleration, denoted by g, is known as acceleration due to gravity. Since it is a vector quantity, it has both magnitude and direction. Its value varies from place to place. Its magnitude is approximately taken to be 9.8 meter per second square, and its direction is vertically downward toward the center of the earth. If the body is projected vertically upward with a certain initial velocity, then also the acceleration due to gravity acts on the body in the vertically downward direction. Since in this case, the velocity and acceleration are oppositely directed. Why? Because the velocity is upward and acceleration is downward. The speed of the body goes on decreasing as time passes till it becomes zero. Therefore, the body starts falling freely under gravity starting from rest. Since the motion under gravity represents motion along a straight line with constant acceleration, all the equations that we have derived and are given in table 1 are also applicable to motion under gravity, with h replacing x, g replacing a, and hn replacing xn. With these replacements, equations in table 1 take the forms shown in table 2. In all the equations given in table 2, h represents the vertical displacement of the body and not the distance covered by it. The body might have covered a distance quite different from h, but at a time t, its displacement from its initial position is h. So this is your table 2 that gives you the different equations for motion and gravity, where the acceleration due to gravity is a constant. It should be noted that all the equations given in table 2 are equally valid for vertically downward motion. If a body is projected vertically upward with an initial velocity, then its acceleration will be in the vertically downward direction, opposite to that of the initial velocity. And hence, g in all such cases should be replaced by minus g. Clear? Now, we come to an example. An elevator is descending with constant acceleration. A person in the elevator drops a coin. At the instant, the elevator starts and observes that the coin hits the floor in 1 second. The coin was 6 feet above the floor of the elevator when it was dropped. Find the acceleration of the elevator. Take g equal to 32 feet per second square. So we have an elevator and man is there. The elevator descends with constant acceleration. The acceleration is not given here. Okay. The person drops a coin. At the instant, the elevator starts. Clear? So suppose this is the elevator. This is the elevator and it starts with an acceleration, suppose A. The man is here. He drops a coin. Okay. At the same time, at the moment, the lift starts moving downward. Initially, the coin was 6 feet above the floor of the elevator. That means this distance was how much? This was 6 feet. And the coin is found to hit the floor in 1 second. You are required to find the acceleration of the elevator. Now, see how it can be solved. Let the acceleration of the elevator be a feet per second square. When the coin is dropped, it falls freely under gravity, starting from rest, with acceleration g. So both the coin and the elevator start their downward motion simultaneously. Hence, the coin can reach the floor of the elevator only if the acceleration of the coin g is greater than that of the elevator, which we have assumed to be equal to a. So the relative acceleration of the coin with respect to the floor is g minus a feet per second square. And the coin reaches the floor at a distance of 6 feet in 1 second. Therefore, using the equation s equal to ut plus half gt square, we have 6 equal to half into g minus a into 1 square. Because u is 0 here, the first term becomes 0. So, taking g equal to 32, we have 32 minus a is equal to 12, or a is 20 feet per second square. Okay. Now, note that only if g is greater than a, that means the acceleration of the coin is greater than that of the lift, the elevator, the coin can hit the floor. Okay. So coin can hit the floor only if g is greater than a. For g less than a, the coin can never hit the floor. This is so because the lift will move with a greater acceleration than that of the coin. So coin will always lag behind the floor of the elevator. So for the coin to hit the floor, its acceleration g must be greater than that of the elevator. Okay. So this is all about the motion in a straight line with constant acceleration and also the motion in the gravity. I assume you like this presentation. यदि आपको मेरा यह प्रेजेंटेशन अच्छा लगा हो तो इसे लाइक करें, शेयर करें और मेरे चैनल को सब्सक्राइब करें. So thank you for watching. See you next time with some other topic of interest. Till then, goodbye.